I'm Pete Zielinski with AdditiveManufacturing.media. We're doing a video series that shows the role of software in realizing the promise of additive manufacturing. I'm with Kevin Brigden of Renishaw. Renishaw is associated with machines for metal additive manufacturing, but the company actually offers a system for metal additive consisting of both equipment and software. So Kevin, the idea we're going to focus on is open parameters. The freedom to fine-tune different settings and techniques of the additive build to get the process just right and reliable for a given production part in a particular alloy. You're going to show us a next step in making use of these parameters, how there's an easy way to experiment with build parameters using an Excel spreadsheet, of all things. So first, get us started. When we talk about the parameters of a build, what kind of parameters do we mean? In metal additive manufacturing, specifically selective laser melting, what aspects of the build do users adjust?
So typically what we're talking about when we talk about parameters is the laser parameters. So how we're controlling the laser and how it interacts with the powder. So that's everything from the power and the hatch distancing between individual vectors, all the way through to how we sort how the laser traverses around the bed. And indeed, when we have multiple laser systems, how we utilize those multiple lasers at any given moment.
For additive manufacturing, Renishaw's software is QuantAM. What's the role of that software?
So QuantAM provides what we would consider to be an end-to-end solution for generating a build.
So I'm going to ask you to share your screen and launch the software, because a point I believe you have to show relates to how when we're experimenting with build parameters, there doesn't have to be a linear sequence. Instead, a user could build an array of parts with lots of different parameter sets to experiment with lots of different variables for how to do the build all at the same time.
So we're in the build environment here of QuantAM. You can see a representation of the build plate that we actually print onto. And in the middle of the plate, we can see an array or 10 density cubes, which form the foundational basis of how we develop materials. And that's a fairly standard thing across the industry. The actual coupons themselves may be slightly different, but the notion is the same. These coupons in particular are primarily aimed for the development of bulk density parameters. So what we're saying there is in the bulk of the material, we're trying to achieve best parameters. Now, we're speaking about parameters again. So what I can do is show you within our material selection window, I've selected a stainless steel material, a 60 micron material. And actually what I can show you is a raft of parameters that are possible to edit for various different scenarios and requirements that, as you can see, there are hundreds of possible settings that a user can change. Now, clearly, when you have so many variables to play with, an organized and deliberate approach, typically relying on design of experiment, is required in order to balance those various different parameters. And so Renishaw identified a need there to massively simplify how we go about doing that. And in principle, what we do is we can actually see, we can bury down into what the various parameters are for any given geometry in that build environment. Okay, that's powerful enough in and of itself, but better yet, as you've alluded to, is that we can actually export this data in the form of a CSV spreadsheet. Here in this spreadsheet, I've created an excerpt of different parameters related to the volume or hatching area of the geometry, and in particular to illustrate the point of how quickly we can create an array of different parameters. All I'm going to do is change the number of borders for those 10 density cubes. So I'm going to select 1, 2, and I'm going to drag through to have a count up to 10. I'm going to save this file. I'm going to return to the QuantAM environment and import that file. And then I can very quickly preview the scan paths that have been generated. As you can see, as I move from left to right across the blocks, that the number of borders increases relative to the setting that was found down here in the material viewer.
So Kevin, that's powerful. I'm watching you change numbers on a spreadsheet, and it changes the path essentially of the build. There are more borders around the outside and less rastering infill as we proceed through those parts. Again, just because of numbers that you changed and allowed to propagate through the spreadsheet quickly. You've been talking about this in terms of materials, in terms of alloys, in terms of working with a new alloy and developing the process that gets the bulk properties just right. Is there an application of this same tool to the geometry of the part? A part with a particularly intricate or difficult geometry, and constructing the build, experimenting with the build, aiming at getting the precision of that part just right?
I think to answer that question, it's probably a good idea to just define some terms as Renishaw uses them, just for the listener's advantage or the viewer's advantage. So what we've spoken about so far would form the bottom portion of this pyramid here, where we're talking about aspects aimed at producing good dense materials. So, parameters such as power, velocity, hatch distance, that kind of thing. As we move up the pyramid, what we start seeing is a degree more specificity for a particular application or use case. So that may be in terms of the strategy that we're actually using to attack the 2D area of a given slice. But then later on, again, when we're talking about multi-laser systems, it's about how we use those systems to divvy up the relative regions of a part, or to talk about how we're going to increase productivity without overly constraining ourselves in terms of where we can use the lasers and when.
A more complex spreadsheet getting at a more sophisticated design of experiments for creating a bigger array of test parts. What are some other common parameters that might be changed in a spreadsheet like that, as customers of yours are experimenting with their own unusual alloys that they're trying to deploy? What kinds of arrays of parameters are they adjusting?
That's an excellent question, and that forms the basis of a good discussion. So the primary layer of parameters, as we were talking about before, this bottom layer of the pyramid I was describing, focuses on these key parameters we can see here. So things such as the velocity the laser is traversing at, the spot diameter, the power of the laser that's being fired, the thickness of the layer, and then the distance between neighboring vectors, also known as the hatch distance. And essentially everything we're doing here is aimed at finding the energy density, and there's an equation that can represent that. So essentially what we're trying to understand is the balance point where we are achieving good density and good productivity without the perhaps negative offsets such as things like keyhole formation or balling up and not getting good welds. So typically a broad material development program will initially focus on these first few parameters and define the bounds within which we can get good results. And then it's a case, as with most things in life, of making it go as fast as we possibly can.
So process development for selective laser melting, it is a trial and error process. It continues to be a trial and error process, but it doesn't have to be time consuming. It's possible to do all of the experiments you need to do all at once.
That's correct. Yeah, you can very rapidly generate arrays and samples of parts. I think an important point to note is that because we're using a spreadsheet interface to import the data, it does mean that the means of generating those data points as input can, of course, be more automated. So I would expect to see elements of machine learning and AI forming future inputs to this. Indeed, I can see scenarios where process monitoring outputs could start coming back round to inform. I think the idea of closed loop processing today is a little far-fetched, if I'm honest. However, I could see that kind of semi-automated process happening very, very soon.
Excellent. Thank you, Kevin.
Thank you, sir.
For more on the kinds of considerations that go into process development for metal additive manufacturing, see the links in the description below. For much more on additive manufacturing technology and how it is changing industry, changing production, visit our website, additivemanufacturing.media.